I am extremely proud to be here and to be given an honorary doctorate. And by the way, in the old times in Italy, there was no doctorate. So this is actually my second doctorate, because the first doctorate came from University of Aalborg. So it seems that people in this corner of the world likes what I've been doing. So thank you very much. So I can indeed put doctor on my slides. So I've been asked to give a sort of perspective on what has happened in the field that I contributed for me, which is called EDA, Electronic Design Automation. And the point is that we started 45, 50 years ago, and the kind of things that we are looking at were transistors. So the basic component that we were dealing with was the transistor. Now, the interesting thing is that if you look at the latest work that we have been proposing, we went from transistor to planets. So we are talking about smart planets and methods to make our planet more intelligent. And so that will be the future. So the past is about transistor, the future is about planets. So this one is the outline of my talk. So by the way, if truth be told, when I was in high school, my career was supposed to be in philosophy. I really enjoy philosophy very much. And I wanted to be a professor of philosophy. A little, I ended up in engineering, but my son is professor of philosophy at Cambridge. So I got a revenge there. But I still like to refer to some of the famous philosophers in what the kind of things we do. And so the main line of the presentation is about an Italian philosopher who's called, of history. It's called Giambattista Vico, who was talking about corsi and recursive. It means that the history always cycles through itself. So it repeats itself infinitely many times. And indeed, in the case of EDA, that is very much the case. And I will show how that is possible. And so again, I would like to mix also some consideration on the technical side and on the algorithmic side with consideration on the business side. Because indeed, some of these fields that we have been fostering, especially in the United States, do have a strong impact in industry, even though serendipitously. Okay, so we didn't plan to fund the industry, we didn't plan to have the big impact that we ended up having on industry, but this is what happened. And so I would like to show you some of that issue. So I said about, things repeating themselves and then cycling through. And there is a Japanese guy, it's a Makimoto-san, he's a good friend of mine. They started saying, well, look, if you look at the IC design field, there's always been a sort of wave that goes back and forth, so it repeats itself infinitely many times. And this is about standardization of electronic circuit and customization. So how often you go from one point to the other is a very interesting phenomenon. And even the latest year, so this is up to 2007, but if you look at the big debate today, is about, does it make sense to develop application-specific standard processors, or you go all with, standard processor, even with many cores? And actually, the very big debate as we speak today is about the fact if you need standard processor repeated infinitely many times equal to itself, or you need special purpose processor mixed to standard processors. So this wave keeps on repeating, even in the latest years. Now, EDA is no different. And actually, the cycles go through two basic topics. That is about analysis and synthesis. And amazingly enough, this is also very much so for many endeavors in science. It's about the fact of analysis, means you try to understand what you have done and to verify if it is correct or not. And synthesis is about building things correct by construction. Now, in general, you cannot synthesize if you don't understand what the heck you do. And so the analysis always precedes synthesis. But after you know how to do certain things by synthesis, you go to analyzing something bigger. And then you go to synthesis. And then you go to analysis again. And every time you do this kind of cycling, you increase the complexity of what you're looking at. And so this wave is also very much followed in EDA. So in fact, it is interesting that the first kind of tools that we develop, and we are talking about between the 60 and the 67. So I started my university work in 66, so I mean it's many, many years ago. But the main topic was how about simulating, so replicating the bench to see if what you have done is correct or not. So it's like you're sitting at a test bench and you're measuring things, except that now you do it virtually, solving equations instead of putting, probes into the circuit itself. So that was the origin of it. And then in the 67 to 74, the components had at most 5 transistors per chip, most, okay, 4 or 5. So now we have billions, right? But at that time, 4 or 5. And now then the big problems were more about at the printed circuit board level, okay, because that was the component that ended up into computers and the like. And so the issue was, can we lay out the circuits and the connections on this plane, the printed circuit board, in an automatic way? Because that took some time to move around the components, draw the wires, and all of that. So that's a synthesis phase. Then when we started doing more integrated circuit, the issue was, are we sure that the layout is manufacturable? And so the analysis is, can we look at the mask and say, are we going to yield when we go to manufacturing? And that was the time of the DRC, ERC. Now, and also that time, believe it or not, in the period between the 70 and the 80, there was a big debate about, can we use parallel processing? Not is the time, okay? We are in the 70s, right? We started thinking about parallel processing then, okay? So parallel processing is an old field. So people now say, oh, parallel computing is great, it's new, and so on and so forth. It's old, it's 40 years old, okay? And many of the mistakes that we did then are repeated today because, people have short memories, they don't read very much, they don't look at what has been done before, and so unfortunately that's what it is. Now, in between the 80 and 87, the question was about laying out big circuits. And we are talking about hundreds of thousands of transistors now, okay? So this, you notice that we started with 4, we are already 100,000, okay? And so can we do that automatically? And the answer was yes. And when we started doing automatic layout of integrated circuit, an entire category of workers disappeared. We didn't need anymore the manual editing of the circuit, so the layout artists disappeared, okay? And that created an improvement in productivity that was not seen before, a tremendous improvement in productivity. At the same time, we started thinking about synthesizing not only the layout, but the logic of the circuit. And if, again, some of you are old enough to remember it, but many of you were not even born at that time, but people were going from a high-level description of what they needed to do logically to the actual gates that were supposed interconnected together to perform that logic function. Now, these were the logic designers, and the work was really miserable. Many errors crept in because of the fact that it was difficult to make sure that the actual gate, when connected together, were doing what they were supposed to do, and then you had to use simulation or logic simulation to do that. Now, I said before, once you know what you're trying to do, then it's time to move to synthesis. And so in that period, logic synthesis was born, okay? So, which means you go to register transfer level description, which is a language description of the logic that you want to implement, to gates automatically and optimally, okay? Meaning that you have very smart algorithms that do that. So lo and behold, in about 10 years, another category of worker disappears. The logic designers nowhere to be seen any longer. And so we got another 100x productivity improvement, and now we are at present day 1 billion transistors, okay? Now, of course, in this time, there is a big issue, again, of parallel processing, meaning big machines that can be used to emulate what an integrated circuit does today. So if you go to Intel, they have hundreds of these machines humming all the time to mimic what the processor would do. But a billion transistors are very difficult to evaluate, right? So that's the reason why you need these special purpose machines. And in fact, if you look at the Cadence revenues, a large amount of revenues from Cadence, which is a 1.4 billion revenue company, comes from selling these machines, which are, again, hardware machines to do simulation. And now there is another interesting wave, which is between standard algorithms and customized algorithms. Now let's look at the issue of circuit simulation. So the standard algorithms, if you look at 5767, was about applying standard methods for solving ordinary differential equations. Because indeed, when you look at the electrical behavior of a circuit, you have ordinary differential equations that you need to solve. Now, at that time, nonlinear ordinary differential equation was very difficult to solve, almost impossible. So by computers, you were just looking at linear circuit and linear equations. Now, in the 67 to 77, and here is when I came to Berkeley, was 75 the first time. And so we work on a circuit simulator, which was open domain. It's called SPICE. I bet that many of you still use SPICE if you are in analog design. And SPICE was an ordinary equation solver specialized for circuit. And actually, if you look at the performance of circuit simulators that were then built up after SPICE, and today you have several companies that are selling their own version of this program. Then you can see that for us, for example, we heard yesterday, Ruzena was saying, well, 17 equations, a big system of equations. We solved 200,000 ordinary differential equations, 200,000 variables, okay? And they're highly nonlinear, okay? So how could we do that? It's by being very, very smart about algorithms, okay? In the 77 to 87, there was a big issue about, the MOS transistors. So everybody moved away from bipolar transistor and went to CMOS. And CMOS for only reason for power. Okay. So CMOS was very compact, wonderful for power. Everybody moved to CMOS. Now, the interesting thing is that MOS transistors, with respect to bipolar transistors, are almost unidirectional, which has a particular effect on the structure of the ordinary differential equation you're trying to solve. And so since they are almost unidirectional, then the idea was, why don't we use relaxation-based algorithms to solve this system of equation? Relaxation-based, you cut all the feedback loops, you imagine that it is all in one direction, you analyze that, and then you close the loop. And then you keep on reiterating, hoping to get to convergence. Now, in general, this method that go back to Newton again, and to Gauss and some very important mathematician of the old times, are very appealing because per iteration, the cost is very small. The problem is that how many iterations you need to reach convergence. Now, because of the fact that you had MOS transistors, then convergence could be reached quickly, okay? And so that was another advance in there. And so FastMOS is actually a customized version of relaxation-based algorithms to solve that. Now, in that time, between 77 and 87, actually my group and I developed a new method for solving differential equation, which was called waveform relaxation. So instead of having a relaxation point by point, we had the relaxation of the functional space. So you're looking at waveform then space or functional spaces. Now it's interesting because this actual method of solving differential equation attracted numerical analysts, pure numerical analysts, we were applied numerical analysts, who decided to open a new field which is called functional iteration. And so if you went to mathematics conferences, they were studying these methods. Okay? So in some sense, we in EDA originated a new field in mathematics, okay, by trying to make things go faster. Okay. Now, what about logic synthesis? Well, again, remember it was born around 77 or so. In 1980, there was a major revolution in the way in which you do the algorithm for logic synthesis. And we use what's called algebraic methods that are actually the basis for design compilers of synopsis and all the optimization methods that you find in tools that you can buy. Now, notice that we keep on oscillating between standard algorithms like dynamic programming, integer linear programming, people optimization, and specialized algorithms like algebraic and BDD-based covering. Now, BDD's binary decision diagram is a way in which you can represent logic circuits. So again, this continuous evolution in cycles. But there is something more which cuts across the different disciplines that I told you is about viscosity and recursive. And so Vico said that there are 3 stages in human history that repeat themselves. And the 3 stages are, the first one is the age of the gods, where Vico said is the human actors of the historical landscape are driven by what they feel, senses, and they are not much guided by reason. Then there is a second age, which is the age of the heroes, where imagination or creativity or novelty or whatever you want to call it is king, right? And then it comes a third phase, or what he calls the age of the man, which is the age of reason. So it's conservatism. So we know what we know, and before we do something new, let's think very carefully. So the conscience of your limitations. Now, the interesting thing that he equated this approach to decadence, right? And then he said, well, every time you have a decadence, then you have a resurgence, and the resurgence starts from the age of gods. And actually, the age of gods is not so nice, if you like, and what you would like to be is always in the age of heroes. Unfortunately, he said we will never be able to do that. Okay. So let's look at another dimension of this coursy and recursive. And it's very interesting because on Sunday, last week, there was an article on New York Times by Clayton Christensen, is a famous Innovator's Dilemma, right, a book. And he quoted that there are 3 types of innovation. One is called empowering innovation. So the technology expands the domain of use and increases employment. So it's a good thing. Now, this one is equivalent of the age of the heroes, if you like, is where you have innovation, deep innovation. Then it's followed by another stage, which is called sustaining innovation, in which what you do is that you bring new products to market which are substituting older products, but it's the same thing, okay? And then the last one is a process innovation, where you actually make the same thing that you used to make before, except much more efficiently. Now, if you look at EDA, really, is about the third thing, right? Is a process innovation. And so we eliminate jobs. But it's also an empowering technology. Why? Because we allow the people who are doing the design to design radically new products. Because you can now do 100 billion transistors that you were not capable to do before, right? So, but again, he said that these cycles, in some sense, it repeats. So, it, of course, doesn't know anything about Vico, but it's the same concept that repeats itself. So, keep this in mind also when you do your work as a PhD student, professor, whatever, about this very interesting phenomenon. So, we said before, the age of the gods is correspond to the 60s and the 70s. Is when you had the small circuits and you were doing the basic things about circuit simulation, PCB layout, system wire writing. Standard cells were started being used at Bell Labs and gate arrays at IBM, so regular layout structures. And so there were some very important work in this period, and so we have the birth of logic simulation and the like. For testing, the IBM D algorithm that actually was generated by a mathematician. So Roth was a mathematician. Now, interesting to know, EDA is one of the very few fields where mathematics and application go like this, right? So it's very, very tightly bound together. And then in terms of the layout stuff, there was, okay, the Gamel from Bell Labs is about the MOTIS or fast MOS simulation. And wire routing was in the 60s, and some of the basic algorithms are still here for us. Again, standard cells from Bell Lab, master slice or gate array were from IBM. And then we go to the business side. Now, during this period, the big companies started thinking about the fact that EDA was strategic for their business, and each one of them invested internally into CAD groups. So every single company had its own CAD group. So there was a very strong Japanese presence, and there was the big companies like IBM and Bell Labs were by far the best. So little things in university, in particular Berkeley with the SPICE simulator, but not much around. And there was a first generation of CAD vendors like Applicon, Calma, Computer Vision. So you never heard of these companies, right? And for good reason, they're all dead, right? And they're not around anymore. But they were selling workstations for people to do that drawing that I was talking about, this mask editing. It was very nice, but not much technology in there. So life cycle of first generation CAD companies, as I said before, they all disappeared. So it's a dinosaur age, right? And so what was the reason why they disappeared? It was difficult to stay abreast of technology due to software complexity and to hardware evolution. So they were selling hardware. Now remember, we are talking about the 60s, the 70s, and the beginning of the 80s, where software was not considered to be of any value. Software was given for free. Okay? Even operating system and the like were free. You buy the machine and you get the software for free. Same here. So you were buying the workstation that they would design. But mind you, one of the big lessons learned, and I think this is a basic innovation that we brought to the industrial market, was that building hardware is expensive. And the margins are small. So where you get your maximum margin is selling software. Now, to make software doesn't cost much. To design costs a lot. But the additional cost for every piece of software that you sell costs nothing. So margins are huge. It's 80% are margin. So it's like, if you talk to an economist, say, oh, how can you do 80%? Well, we can, right? Because it's software. So also little customer loyalty is due to the low-level technology. There was not much technology in there. So that's the reason why they went away. In addition, they were incapable to read the market. They were not seeing these tectonic shifts about what was important, what was not important. So they died. Okay. So the age of heroes. Now, this is a great period of EDA. So vibrant period for creativity, expansion both in research outcome and industrial development. So these are the kind of big contributions that were brought to bear in this period. Now, in this period, every single person who was anyone in computer science did work in EDA, partly. Even people like Dick Karp, who's a very deep theoretical guy, had papers on automatic layout. Okay, so that's kind of interesting to note, because this new field was attracting a lot of other people from different fields, right? We're coming to it. Now, for Ruzena, Randy Katz was doing only this, and Carlos Sequen was doing EDA stuff. So everybody plus his brother was doing EDA. Okay. Now, in this period, there was also some things that I put in question marks. So expertise system and neural networks. Now, why did I put this question mark? In my opinion, this is a gigantic fraud, right? It's horrible things that never worked, okay? And so at that time, everybody was, oh, new algorithms, let's try to use them. If you look at papers published in the 80s in the major conferences, were full of expert system this, expert system that, and neural network here and neural network there. And they didn't have any basic science in it, and so they disappear like the dinosaurs before. If you look at the conferences of the past 10 years, you don't even find the word expert system or neural networks, okay? So beware of fads, right? Fads are bad. And so the largest vendors today were formed in this period. So Cadence and Synopsys were in the 80s. So very basic stuff, relaxation-based techniques, as I said, we were among the basic proposers of this. And in this period, the PDD method of representing logic function was also introduced. And here, the first time that people started talking about formal method or formal verification was during this period. So now if you look at computer science, theoretical computer science, there is a lot of interest or attention to formal verification. Now there is even a conference called CAV, Computer-Aided Verification Conference, but the origin is here, okay? Again, it's a new field in computer science was born in EDA. And the reason is because, again, this tight interaction between the practical problem and the application and the theoretical algorithms. So on layout, all kind of very interesting stuff. It was Osterhout and Newton, Caltech and Bell Labs, silicon compilers. Now at this time, it was a very important event. It was the so-called Mead and Conway approach to IC design. So again, some of you may not even heard about these methods, but the idea was that indeed to design integrated circuit was no difference than designing a compiler for software. And so you could go from a high-level description of what you wanted to do into actual layout. Now the only problem, and they formed companies out of this idea, so Silicon Compiler was one such company, but guess what? You know, they didn't have much following later on. They all disappeared, the silicon compilation-based company, and the reason was that there was no attention to optimization. So it was just transformation from one layer of abstraction to the next, with no attention to try to make it better or optimized. And so it was not a mathematics-based approach, it was a computer science-based approach. And in fact, the people who really got excited about this method were the computer science department. And so in fact, there were courses of IC design that were taught by computer science departments. Okay? And so every computer scientist felt that they could design an integrated circuit. Now, for those of you who are rooted in physics, you know that this is quite difficult. And designing integrated circuits that do something useful is certainly not as simple as pushing a button and here the circuit comes. And so that was a bad turn of the technology, even though the good thing, what was the good thing? The good thing was that a lot of people got attracted to the field because of the simplification that was made by Carver Mead, that, by the way, is a physicist, and he does know how difficult it is to design circuits. Okay. So what else was happening here? Logic synthesis systems, espresso. Now you know where espresso comes from, given the name. You know. So in that time we use a lot of Italian names all over the place. Okay. No, that's for some obvious reason. And then all kind of different approaches that were quite interesting came to bear. And mind you, the optimization algorithms that were embedded in the system that we put together were all here, NP hard, okay? Now, every time you take a theoretical computer class or an algorithm class and say, oh my God, NP complete problems or NP hard problems, impossible to solve. This is wrong, okay? Never believe that, because otherwise you stop solving interesting problems. What it says is that there is no algorithm known to man that can solve this problem in all instances in polynomial time. Now, notice why I'm saying in all instances. It means that if you know more about the problem, you can search heuristics in the way in which you search the space that make this calculation go fast. Okay? So in fact, all the logic synthesis algorithms known to man have a sub-problem, NP-hard problems, and they are solved just fine. And we can, again, we can synthesize easily 1 million gate And so if you think about, exponentially bound algorithm with 1 million input objects, you think, well, it's never going to happen, right? Wrong, okay? So don't think that impossibility on the theory side implies that you cannot solve the problem. I would even venture that some of the problems that we are meeting today in system design, they are undecidable. So for those of you who know something about computer science, undecidable is forget to the power of n, right? So forget it, no way. Well, we solve that as well. And how come? Because we can say, if you solve a problem, if you arrive to a solution, you know that you got a solution. So the problem is that if you don't get a solution, maybe you may get it later on, or you may never get it. So what you do is you call it quits and you say, I don't know how to solve this problem. So this is a practical approach to things like undecidability. So if you can get something, it's good. And if you know the nature of your problem, more often than not, you get an answer. Okay, so don't give up. Okay, please don't give up. And when you see a difficult problem, it's good a chance of making very nice publications. Okay, so actually you should be very happy that you have a very difficult problem. Okay, so all right. Moving right along, at this time there was hardware description languages and became a major battle between two different languages. Now, it's very interesting because when you grow gray hair and you've been part of all of this, you see things in perspective. And so all this debate, will be, horrendous debate in panels and people going at each other's throat. And Europe versus United States is about this Verilog versus VHDL. VHDL was actually originated in the United States, but was espoused by Europe a lot. And they were two languages, right? They were completely equivalent, okay? But people will kill each other to do something like this. And so here is my friend Joe Costello was a CEO of Cadence 1995. Adoption of VHDL was one of the biggest mistakes in the history of design automation, causing users and EDA vendors to waste hundreds of millions of dollars. In fact, VHDL now has almost disappeared, and most of the people use Verilog or System Verilog or what have you. But doesn't matter. Could have been VHDL and not Verilog. Doesn't make a damn difference. They are equivalent, especially if you do things automatically. Who cares, right? And so this, don't spend your life on useless things. This is a useless thing, okay? So don't do it, all right? So do the difficult problems, don't do the stupid stuff, okay? That's great, all right. So in the age of the heroes was also the construction of these parallel machines that are still going on very strong. And then you start talking about high-level synthesis and the like. Now, this is a very interesting point because you would say, well, after you have done gates, and you go from register transfer level to layout in automatic fashion, why can't we go even one level above and synthesize architectures? So now the point is that you have a very high-level function, and you want to find out what is the best composition of weird objects that can give you an optimized solution. This is called high-level synthesis. Now, still today is an unsolved problem. So there are tools that you can buy out there, but not very much sold because people don't trust this level of automation, because not much mathematical advances have been made in the past few years. Now, I told you that this period of the hero, everybody plus his brother was writing papers in this domain. And in fact, if you look at the libraries, then you see that the most cited papers in computer science 2005 were 3 papers in EDA, 1, 2, 3, okay? Most cited in computer science, okay? Interesting. Now, business-wise, what happened there? So Workstation Companies were born, and they were called Daisy, Mentor, and Valid. And they were doing schematic data capture, which means, the schematic of gates, right? So you would do logic design. Now, remember what happened to the Calma, Applicon, and so on. They disappeared because they were doing mask editing. Now, you can imagine about this kind of companies where they ended up. But these were doing schematic data capture, and they were selling hardware again, okay? Now, pure software companies. Aha! Now we get it, okay? So we were the first one to propose a purely software company, SDA, 1983. They merged with ECAD into forming Cadence, okay? Now, Silicon Compilers as well, Silicon Design Lab, ViewLogic, Gateway, OSI. Now, OSI is called Optimal Solution, Inc. Now, the quiz is what this company became. Later on, became Synopsys. Okay, I can give you that solution right now. But these were software-only companies. So not sell the hardware, just sell the software. Okay, and in fact, they prevailed. So quiz already gave you a solution. And during this time, were also the acceleration companies. Companies were building specialized hardware to solve the emulation problem. Now, during this period, not only new companies were formed, but everybody plus his brother had his own internal CAD group. And so if you look at the amount of money that was spent in EDA, was in the several hundred to couple of $1 billion spent in this domain. So a lot of money. IBM and Bell Labs at this point really had the technical leadership in the industrial world by leaps and bounds, really very strong solution. And at this point, strong groups in universities, because notice all the computer scientists were doing EDA, and so some of their students were focalizing on this EDA stuff, and so our own students got hired everywhere. So, my students ended up MIT, Stanford, CMU, you name it. So we populated the world with EDA people. So company life cycle, second generation business model, proven not sustainable due to the domination of general purpose workstation. So people who were building their own workstation disappeared. And so now you have Silicon Compilers, Silicon Design Labs also disappeared because we say before Silicon Compilation was not interested in optimizing the final results of the circuit, and guess what? People didn't buy this kind of approach. All right. So now we come to the age of man, 1993, 2012, and you can imagine that the age of man is about consolidation of what was done before. So no new fields, okay, in EDA per se. So when you start continue designing integrated circuit, there has not been a fundamental innovation. So now you know how to do things better and better and better and better, but the products are always essentially the same, right? Automatic layout, logic synthesis, that's it, and parallel machines to validate big system. More or less, that's what we have to deal with. Now, so scientific relevance, 2012, what happened there? Well, we have 3 famous papers still up there, but much lower, right? Which means that computer scientists stop really investing into this field. On the other hand, if you look at the quotation about architecture, right? So your truly is number 1, okay, in the citation for hardware and architectures. And number 2 is John Hennessy at Stanford. But look at number 3, 4, and 5 are all CAD-like people. Randy Bryan now is an administrator, is the dean of the College of Computer Science, but that's what it is. So yes, the computer scientists are not there, but some of us have become, by definition, computer scientists. Now, there have been also some significant advances in algorithms, and the name of the game in algorithms, since we are doing the same things, but we want to do them better and better, is about reduction of complexity. So in the ordinary differential equation domain, if you like, in circuit simulation, it's still very much used everywhere. The name of the game is that how can you reduce the number of equations to speed up the execution of the simulation engine. So model order reduction methods were coming of age. And so some of the most important contribution in model order reduction techniques came from EDA. And so this is again the interaction between numerical analysis and EDA. So, okay. And there are some very, very clever and elegant methods. This is the number of applications that you see. Now the time is running short, so I will not analyze each one of them. But is it's very interesting that still advances can be had. And it's not a completely novel field, but nice thing could be done. So formal verification, as I said before, is having a fundamental impact also in other fields, like system level design, computer program verification, the like, is really very important. And one of the points is the speed increase. This one is a logarithmic scale, right? So between 2000 and 2012, you had 3 orders of magnitude speed up. Okay, 3 orders, 1,000 times. Okay, still the same problem, satisfiability. How come you can do it 1,000 times better? Because you know more about the problem. And so you can apply heuristics to visit the state space, not giving up the optimality of the solution, but doing it faster. Okay? So the heuristics are related to the way in which you explore the space, not about heuristic in terms of getting to the solution. Okay? And so this is a very important topic because it changes dramatically the name of the game. Things that you didn't think it was possible to do, now you can do it because you have a tool that goes 1,000 times faster than what you had before. So all kind of very interesting stuff. For example, property-directed abstraction, automatic abstraction. Now notice that, and this is something I'm very dear to my heart. If you look at methods of solving problems, since man was born, there are 2 basic techniques. One is divide and conquer, so break the big problem into smaller pieces, and the second one, use abstraction. So eliminate unnecessary details, right? So unfortunately, both of these, in general, are best done by men. We don't know how to do it very well automatically. So in fact, decomposition is one of the most difficult things to do. Right? So and taking into consideration all the aspects of the problem and so on. Now, abstraction is similar in terms because you have to decide what is immaterial, what is not important in the problem you're looking at. Well, model order reduction is a way of abstracting without losing the quality of the final answer. Similar things you can say about abstraction in the logic domain. And now, once you start understanding what it is, you can do it automatically again. This is a great thing, right? So this is possibly the most important advance in this domain, is this automatic abstraction thing. So I won't bother you with the layout advances, very interesting stuff, but no time to go through it, because I want to go to the business challenges, and we'll stop here. Given time, I will not be able to say much about the future. So to stay alive and prosper is a major challenge, and so you must adapt to changing business condition and structure, changing client-vendor relationship, and changing technology. So mammals have been able to do that, right? So dinosaurs, no, so they died. Mammals still around. So that's the idea. So, but you must extend to other fields. And so the name of the game, for the past 20 years, I've not done integrated circuit anymore. I'm doing big systems, okay? And so the method for designing cars, airplanes, health systems, and the like, are the frontier of this method, not any longer integrated circuit. That's good. You should focus on some of it, but the big gains are to be had in different domains. Also from industrial point of view. Now, interesting point is that now we are in a monopoly, or in a oligarchy, in an oligopoly, meaning that we have only 3 major companies that dominate about 87 to 90% of the market of EDA are in 3 companies only. And the interesting thing, you see the green bubble is system. Now, that is still to be gain, right? So the field itself is growing like this in terms of the market, and the stranglehold of single company is small. So it's a great opportunity to go. By the way, EDA market is growing, still growing, believe it or not. And you know why it's growing? We say that we need to extend to other markets. Now you have 2 ways of extending to other markets. One, you do new things, and the other thing is you get new people. You know where we sell now, besides the standard EDA companies? Give me some names. Anybody is venturing to bet where, to guess where the world is going in that domain? Is very strange, very strange. You know who's buying tons of tools? Is Amazon, Oracle, Google, okay? Integrated circuit. That's where the world is going. You know, these big companies are very much afraid that strategically they may be cut off from integrated circuit manufacturing. And so all these companies, Apple, by the way, Apple is very well known, and the latest products are based on some of the processors they design. Okay, this is a very important point. Remember this, the world is changing. Okay, so you extend it to new people in this particular case. Now, notice that from an industrial point of view, the latest company IPO was NASDAQ, and that was 2002. So 10 years, no IPO in EDA. But look at this. So these are EDA acquisitions. So in the last 10 years, there have been 150 companies being acquired, right? So keeps on going, right, forever, right? And so this is interesting because it's a consolidation. So when you look at Europe, one of the things that I always say is bad in Europe is that there is not enough consolidation of the small and medium companies into larger companies. And by the same token, the large companies are dinosaurs that refuse to die and will take us down. You know, so that's another important message: is that companies grow, they become big, they decline, and they disappear. Right? So there is no reason whatsoever why you should keep alive dinosaur companies. So the role of innovation in EDA is interesting because the acquisition model cannot last forever. Startups cannot solve problems that involve substantial resources, so you must invest. I mean, you must invest some kind of way of doing innovation. This is a dilemma. The innovator's dilemma is right here. It's a cannibalization of what you do in order to stay alive. And so it's like, you know, today I feel like we are trying to use the bicycle to get to the galaxy, right? That's not the right tool to go there. Okay, so since we are above time, I will not tell you what the future is, but the future is about the smarter planets that we are talking about. So I write just about today, right? The future is talking about how you design things that have a deployment that go beyond countries, beyond company boundaries, is really a radical revolution. And this is made possible by the introduction of a myriad of sensors and computing devices that are so small. Now we are down to 20 nanometers, but we are going to go down to 7 nanometers in a few years. And so now you can imagine how many chips you can populate the world with. And now the point is that now you have a tremendous platform, and you have to program this platform to solve the world's real important problems. And so that's where the future of EDA and design methods in general is going to be. Thank you very much.